So thank you very much to the organizers for this great conference, and thank you for inviting me. It's a pleasure to be here because it's Damien's conference birthday, and so it's also a way for me to say thank you for this great supervision, and thank you for being a nice person as well as an incredible mathematician. And okay, now let's talk about maths. And today I want to talk to you about subgroup mixing in Baum-Slack solitaire groups. So before going into the details, I want to give you an overview of what's going on. So if you don't know Baum-Slack solitaire groups, you can just think of them as a class of groups acting on trees. And by subgroup mixing, I mean that I'm interested in the dynamics induced by the conjugation action on the space of subgroups. So more precisely, it means that we want to quantify to what extent the conjugation action, so of some countable group, on its set of subgroups, is, with a lot of dotted marks, chaotic. And is topologically chaotic, in fact. Okay, so topologically means that we will put a topology on the set of subgroups. This will be more precise in my first part. Topology, sorry. And by chaotic, you can think about topological analogs of ergodicity or mixing. So. And so what is the framework? We will be interested in two main axes. The first one is finding invariant partitions of the set of subgroups of G with a nice topology. For G being in this particular class of groups. And the second question will be to quantify to what extent the action of G on each piece of the partition is chaotic in the sense which will be made more precise in a few minutes. Okay, so let's start. Okay, so what is this topology on the space of subgroups? So first of all, the setting is the following. In my talk, G will be any countable group, infinite countable. Okay. So this is what we call the Chabotti topology. And this is given by the natural inclusion of the set of subgroups. So the subsets of G, which are subgroups, into the Kendra set. So ended with the product topology, you have a Cantor set here. And as being a subgroup is a closed condition, it's just an intersection of cylinders. This is a closed subset, in fact, of the Cantor set. Okay. And if you want to describe a basis of neighborhoods, this will be parameterized by finite subsets of G. I'm just writing in another way the basis of cylinders given by this. And the associated open set, so for any O and I finite subsets of G, will be the set of subgroups such that the two following conditions hold. So H contains I, and H intersects O trivially. And finally, if you don't like basis of neighborhoods, you can just think of this topology as the topology of the simple convergence. So that is to say a sequence of subgroups Hn tends to a subgroup H as n tends to infinity. If and only if the two following conditions hold. For every H in H, H belongs to Hn for n large enough. And same for every H which is not in H. Okay, so to be sure the definitions are clear, let's take a look at some examples. So let's say you want to study up to homeomorphism, the set of subgroups of Z. So what is a subgroup of Z? It is either trivial, or it is of the form NZ, for some n non-zero. And as the trivial group is a limit as n tends to infinity to the subgroups NZ, you have a picture like this. And each of these are isolated. And if you want to, let's say, to do the same with the set of subgroups of Z2, you have something a bit more subtle, maybe. You always have the trivial group here, which is a limit of rank 1 subgroups. So of subgroups of the form ZU for some U in Z2 non-zero. So let's say this type of subgroups will be like this. Each of them are isolated among rank 1 subgroups by basically the same argument. And each of them will be limits of finite index subgroups, because you always can find a complement and make this complement tends to 0 with the same trick. So you'll have a picture like this, with the crosses being finite index subgroups. And in fact, what we use is a particular case of the following proposition. And let's say it's an instructive exercise. If G is finitely generated, finite index subgroups are isolated. Any question? Okay, nice. So now let's talk about dynamics. Okay. So I will define the notions of chaos we'll be interested in. So here, X is a Polish space, and you can take it to be the set of subgroups. and G acts on X by homeomorphisms. And you can think of this as being the conjugation action. Okay, so definition. The action of G on X is called topologically transitive. If the following holds, so for any two non-empty open subsets U and V of X, there exists a G such that up to applying G to U, they intersect non-trivially. So the picture is the following. You have an open set here, U, you have an open set here, V, maybe they intersect trivially, but there exists some G such that when you apply G to U, you get a non-trivial intersection here. Okay. I said that the action of G, and we will abbreviate it by GT. So the action of G on X is highly topologically transitive. Which we will abbreviate by HTT. If for any non-zero integer n, the induced diagonal action of G on Xn is topologically transitive. So what's the picture here? It means that whenever you pick U1, etc., Un non-empty open subsets, and V1, etc., Vn non-empty open subsets, there exists a G, which is the same for everyone, such that up to applying G, you get a non-trivial intersection here, etc., and you get a non-trivial intersection, GU1 here. So this is stronger. And we have something even stronger than this, a property which is even stronger, which is the notion of topological mixing. And so to define it, I need to pick any probability measure mu on G. And I will denote by GK the random walk with step distribution mu. And I say that the action of G on X is topologically mu mixing. If the limit as k tends to infinity, so for any non-empty open subsets of X, so non-empty open, the limit as k tends to infinity of the probability that G1, etc., Gk applied to U intersects V non-trivially is 1. So this means that in the first definition of topological transitivity, the following holds for a lot of G's, and a lot of being encoded by random walks, by elements asymptotically produced by random walks. Okay, and so topological mixing implies high topological transitivity. Okay. So we will be interested in quantifying where the action is among these three notions of chaos. For invariant subsets of the set of subgroups of G, which I will write this here. Okay, but asking for topological transitivity on the set of subgroups of G is too much because finite index subgroups are isolated. And so you can't hope topological transitivity on the whole set of subgroups. So in fact, at least we have to restrict to the set of infinite index subgroups. Sometimes there are obstructions for being topological transitive on this whole set. Sometimes it's just too complicated to study the whole set, and so we will sometimes restrict to subset of this. And now I want to give the state of the art concerning groups acting of trees. So in this section, question? Okay. In this section, G is a group that acts, so infinite countable, on an oriented tree, T. And I will follow two main axes. The first one is the case where stabilizers are small when they vanish at infinity. And the second one will be a case of a class of groups that typically doesn't satisfy this condition, and this will be the Wamsack-Soita groups. Okay, so we ask also that the action is minimal and irreducible. Just to mature, it's not a stupid action. And so the first axis of small stabilizers will be the case of acylindrical actions. Okay. So in this section, we assume that G acts on T such that the induced action is acylindrical, which means the following. There exists an R such that the stabilizer of any edge path of length larger than R is finite. So this means that the vertex stabilizers need not be finite, but whenever you take a path which is large enough, this becomes finite. And in this setting, we have a result from Penelope Azuelos and Damien Gaborio. In 2004, yes, I think, which tells you the following. They proved that the set of subgroups that act non-co-compactly on T, so which I will denote by the following notation. So the set of subgroups H such that the quotient graph is infinite, it's an infinite graph. So they proved two facts. The first one was that this is a Cantor set, so we are studying a very large subset of the set of infinite index subgroups. And they proved that if G contains no non-trivial normal subgroup, no non-trivial finite normal subgroup, sorry, then the induced action is highly topologically transitive. So this is the first positive result I wanted to talk to you about. And the second one is a result from Hall, Minassian, and Osin. Which tells you that in the same setting, so this, we're in the case of an acylindrical action, so in the same setting, if G has no non-trivial finite normal subgroup, then the action of G on a smaller subset than the one in the previous theorem, which is the set of quasi-convex infinite index subgroups. So before defining it, I finished that theorem, is topologically mu mixing. For any probability measure mu with finite, symmetric, and generating support. And so what is this space? This is the set of subgroups H, such that, so first of all, H is an infinite index subgroup of G. H acts on T properly, which means that the vertex stabilizers under the H action are finite. And the H orbits are quasi-convex. Which means that whenever you take two vertices which are close from an H orbit, then the geodesic between those points is also close. Okay, so the philosophy of this result is the following. Small stabilizer implies huge disorder on the level of the set of subgroups. And then I want to explore another axis, which is the case of typical examples of non-acylindrical actions. Sorry. Not necessarily. I don't think we know something about the topology. The action remains mu mixing on its closure. Sometimes this is dense in this set. Sometimes not. Thank you. Okay. So, Bam-Saxoita groups. So maybe this is a good time to give a definition of them. Okay, so Banach-Sachs-Victor groups are parameterized by two non-zero integers. And they're defined by the following presentation. There are two generated and one related. So this is the simplest case of an HNN extension of Z over Z. And I won't define this, but they act on what we call their Basser tree, TMN, which is the oriented tree, all of whose vertices have M incoming edges and N outgoing edges. And the important thing about this action is the following. So first of all, this is transitive. And the second thing is that the vertex stabilizers are conjugate to the subgroup generated by B, and this is torsion-free. And the edge stabilizers are conjugate to the subgroup generated by BM. In particular, the fact that this has finite index in this implies that the stabilizer of any finite subtree is infinite cyclic. So we're typically, in the case of a non-acylindrical action, it can be infinite. It can be finite, sorry. And in this setting, Alessandro Carderi, Damien Gaborio, François Lemaître, and Yves Stalder proved that this led to a very different situation on the level of the set of subgroups. And to alleviate notations, from now I will assume that M is different from N in absolute value, and that M and N are larger than 1. Okay, so they prove that in this setting we have a partition of the set of infinite index subgroups. So G is equal to, G is equal to BSMN. And so they uncovered an invariant partition of this set into one particular piece I will talk it about later, and a collection of open subsets. So these are open. This one is closed, which is invariant. And so the first remark is that as soon as you have disjoint open subsets, this prevents the action from being topologically transitive on the whole set. However, so this is the negative result compared to the previous one. However, they proved that, so this is an invariant partition, that the G action on each piece is highly topologically transitive for every L, either an integer or infinite. And so from this result, the following natural question arises: is it mu mixing? Is it topologically mu mixing? And these are the two theorems I want to talk to you about today. Oh. Okay, so question. Is it topologically mimixing? And the answer is no in general. And this is encoded by the two following theorems. I just will prove one of them. So we're still in the setting where m is different from n in absolute value. And in this case, there exists a continuum of probability measures. Oh, sorry. So this is from me. With finite symmetric generating support. In fact, there will be the standard generators here, BB minus 1, TT minus 1. Such that for any open piece of the partition, so I exclude L equals to infinity, the conjugation action on this piece is not topologically mimixing. And the second theorem, so this is a negative result, and it proves that the high topological transitivity obtained by Carderi-Gaboriau, Lemaitre, and Stalder is optimal in the case of L non-infinite. And the positive result is the following. For any probability measure with finite symmetric generating support, the conjugation action of G on K infinity is topologically mimixing. So in Hall, Minassian, and Austin's article, they uncovered an example of a highly topologically transitive action, which is, a highly topologically transitive action which is not topologically mimixing in a different setting as the set of subgroups. So to my knowledge, this is the first example known in this framework. However, the measure we will build is not symmetric. It has symmetric support, but it's not symmetric. So maybe this is still an open problem. And in the remaining time, I would like to give some ideas of the proof of the first theorem, unless there are some questions. Yes?
So in theorem 1, we can find many measures mu such that it's not topologically mimixing.
Yes.
Is it possible to find measures such that it is topologically not?
Maybe.
Is topologically mimixing?
Maybe it's not clear.
Okay, thanks.
Thanks for the question. Any other questions? Okay, so let's move to the proof. Okay, so from now we will focus on the first theorem because this is the most surprising one. Okay, so remember the setting is the following. M is different from n in absolute value. In particular, this means that there exists a prime number p such that the p-adic valuation of m is different from the p-adic valuation of n. And without losing generality, we can assume that, in fact, the p-adic valuation of m is strictly larger than the p-adic valuation of n. And from this observation, we impose one condition on the support of mu. We want that we want it to be supported on b minus 1, t minus 1. Each of these generators having non-zero measure. And from this, we also impose this condition. And I didn't give the definition of the KL because it's quite tricky and not very useful. But we just have something to use about them, which I will state here. P is a prime number. Yes, so P is prime. And this is the largest n such that Pn divides m. Thank you. Okay, so claim this is the only thing to know about the KLs. So the goal is the following. We want to show that the conjugation action G in KL under these assumptions on mu is not topologically mu mixing. Okay, and so the claim is that there exists an integer, let's say q, such that the p-adic valuation of q is strictly larger than the one of n, which I remind you is larger than the one of n, and the set of subgroups H such that the intersection of H with the generator B is equal to BQ. So as Q is non-zero, this is an open set. And the claim is that this set is included in the KL. And this is all what we need. OK. And so as this is an open set, this will be a candidate to highlight non-topologically mu mixing situation. So let's call it U. And we will show that, so GK is the random walk on BSMN with step distribution, this measure. And yeah, the goal is the following. You want to prove that the probability that G1, etc., Gk apply to you, so apply to you means conjugating. The probability that this is empty for k large enough, which is a negation of topological mu mixing, is non-zero. And this will lead to the conclusion. Okay. And so this results from an observation concerning which is implied by the relation of your group, which is the following. So observation. If lambda intersects B, say in some BL, and its conjugate under T intersects B into some BL prime, then we have an equation that relates L prime to L. Then we have that L divided by its greatest common divisor with N is equal to L prime divided by its greatest common divisor with M. And so we will use this and the fact that the p-adic valuation is huge to obtain contradiction. Okay, so as I am not a probabilist, I will prove a deterministic result and then show that this happens with non-zero probability. So the deterministic result is the following. I take a sequence of elements in B, B minus 1, T, T minus 1, such that for every integer k, the number of occurrences of t in the k first terms is strictly larger than the number of occurrences of t minus 1 in the first terms. And this I will call it hk plus, and this one hk minus. And so using the previous equation and these assumptions on the p-adic valuation, we can show by induction on k such that if lambda intersects B in BQ, then it's conjugate under this product. Oh, sorry, these are still elements of the group. And then there will be a realizations of the random walk. Will be some BQ prime with Q prime P equals to QP plus hk plus minus hk minus np minus np. Okay, and then what happens? So as the measure of t is strictly larger than the measure of t minus 1, this happens with non-zero probability. And under this assumption, this quantity tends to infinity asymptotically almost surely. And so you have that at some point, this will be too large for this group to belong to U. And so we're done. In the remaining 3 minutes, maybe I can give just an idea of the proof of the second theorem. So yes, first a question. Here, this fact was crucial. And so, question, what happens if the measure is non-biased? Okay, and so one word about the idea of the proof of the second theorem. So it relies on, so the crucial point is to relate the action by conjugation of the set of subgroup and the action of the group on the Basset tree. And then when you highlighted this link, you can use a result from Cartwright and Soardi, 1989, which tells you that the random walk on the Basset tree asymptotically almost surely tends to a random end. And using this and making the link with the space of subgroups, there are still work to do. You can prove that, in fact, this implies mu mixing for any suitable probability measure. And oh yes, good question. This is the only piece which is easy to define. It is the set of subgroups H that intersect B trivially. So that act freely on the Basset tree. And thank you for your attention. I think I'll stop here.